In this video, I'll define center and periphery. We'll take a look at a couple examples of determining the center and periphery of a graph. And finally, we'll look at Theorem 2.9, which tells us that every graph is the center of some graph. So what's the center of a graph? Well, it's the collection of all those vertices which are central. Rather, more specifically, it's the induced subgraph by those vertices. So let's say let S be the set of all central vertices of a graph G. Remember, a central vertex is a vertex whose eccentricity is the radius of the graph, so the minimum possible eccentricity. Then if we induce a subgraph by S, is the center of the graph. So we denote this by center of G equal to G of S. So the subgraph induced by those vertices. So that's center. And then remember, as opposed to a central vertex, our other notion. So right, central vertex is a vertex that achieves the minimum eccentricity. And a peripheral vertex is a vertex that achieves the maximum eccentricity, right? A vertex whose eccentricity is the diameter of the graph. So I'll say let T be the set of all peripheral vertices of G. Then G of T is the periphery of G. And we denote this per of G. So that would be G T. Subgraph induced by all the peripheral vertices. So, okay, so how do I determine the center and periphery of a graph? Well, it'll help to know, right, what the eccentricities of all the vertices are. So let's just go through computing all the eccentricities of these vertices. So V1 here, distance 1 to each of those outside vertices, 1, 2, 1, 2. Looks like I can get to every vertex in at least 2 steps by either just jumping to them if it's adjacent or coming down to one of these vertices and then jumping to them. So it looks like these all have eccentricity 2. And then finally, these inner vertices. So let's see. Right. Yes, think about this for a second. I can certainly get from U1 to any of these, the V1, V2, or V3 in 2 steps. It's adjacent to U3 and U2, so its distance there is 1, distance 2 there. What about from U1 to, say, U5? 1, 2, 3. I can do it in 3 steps. 1, 2, 3, 1, 2, 3. Looks like the best I can do is do this in 3 steps. So U1 and U5 here, it looks like would be antipodal vertices. By symmetry, the rest of these inside vertices also have eccentricity 3. So my V2, V1, and V3, these are my central vertices, even though it looks like they're on the exterior of this graph. But again, this doesn't really matter. We could easily flip these so that they're on the interior by just redrawing it. So there's my central vertices, and then my periphery would be the subgraph induced by these vertices. So let's see, what's the center then? So the center of G is this graph. So induce the subgraph on V1, V2, and V3. I guess let me say, so central vertices are V1, V2, V3. So now induce that subgraph. I have V1, V2, V3. So it looks like the center of G is K3. It's that triangle. Periphery of G then is the subgraph induced by the peripheral vertices. So there would be the periphery of the graph. So not too bad. Once you get the hang of finding eccentricities, it's not too bad to pick out the center and periphery. Right, take a look at a couple more examples here. In particular, we looked at the odd order paths and even order paths. Let's take a look at those again. So if I have a path, say P2k plus 1, so if I have an odd number of vertices, let's say k is, let's let k be 2, just as a for instance, 3, 4, 5. Remember we computed eccentricities, 1, 2, 3, 4, eccentricity 4, 3, 3, 2. So now this would be my central vertex, and these would be peripheral vertices. So the center of P5 is just K1. Just this graph, so K1. The trivial graph. And the periphery of P5, well, it's that vertex. And that vertex, when I induce the subgraph from this, I see I just have two disjoint K1, so this would be 2K1. And it's not too hard to see that that's going to that's going to generalize as well, that'll generalize for any odd order, that the center is always going to be the one vertex in the middle, the periphery is going to be the two vertices on the outside. So what about even paths? So look at P2k, and let's just take k equals 2, for instance, and then generalize on this. So eccentricities, this would be 3, 3, 2, 2 for my eccentricities. Now these would be my central vertices, and again these would be the peripheral vertices. So the center of P4 is K2. It's K2, subgraph induced by these two, they have an edge between them, and the periphery again of P4 would be 2K1. So in general, this is going to hold that the center of P2k plus 1 is equal to K1. Center of P2k is just going to be K2. And periphery as well, periphery of any path, so I'll just say Pn is 2K1. Okay, so I'll share one theorem here. This is Theorem 2.9. That every graph is the center of some graph. So that is, if I have some graph G, and I want to know, can this be the center of another graph? Is this ever the center of another graph? The answer is yes. We can always build a graph, no matter what graph you give me. So let's start proving this. I can always build a graph so that that graph is the center of the other graph. So proof, let G be a graph. And we'll construct a graph H such that G is equal to the center of H. So, okay, so how do we do this? I'm not going to write down all the things, right? You can read this. I'll just draw it here. So here's my graph G. I'll just draw it as a blob here, right? There's some edges going on in here. That's my graph G. What I'll do is I'll take two new vertices and I will join them to G. So I'm going to make an edge between this vertex, let's call it U, and every vertex of G, and a vertex V, and make that adjacent to every vertex of G as well. And then finally, I'm going to take another vertex V1 and make it adjacent to V. I'll take another vertex U1 and make it adjacent to U. So I claim that, so this would be my graph H now, that the center of H is equal to G. Okay. So I want to show that the center of H is equal to G. That means I need to show that the vertices of G all have the minimum eccentricity over the whole graph. So let's go ahead and start computing eccentricities of vertices. So I'll start over here at U1. To get from so U1 to U, that's obviously distance 1 between them. U1 to anything in the graph, well, I can just go to U, since U's adjacent to everything in G. It'll take 2 steps to get anywhere in G. And then let's see, if I want to get from, so distance from U1 to anything in G is 2. So if I want to get from U1 to, say, V, I'll have to do that in 3 steps, right? 1, 2, 3. And if I want to get to V1, that'll take 4. So it looks like U1 and V1 both have eccentricity 4. These will turn out to be the periphery of G. Okay, so let's see. U, 1 to that. 1, 2, 3. It takes 3 steps to get to V1. That's the furthest vertex away. And same thing here for V. So what about my vertices in here in G? What's the eccentricity of any one of these? So to get from any vertex in G to another vertex of G, how do I do this? Well, I take the vertex to U and then U to this other vertex. So I can get there in 2 steps. So between any 2 vertices of G, I can do 2. My distance is 2. And then I can also get from any vertex of G to any one of these in at most 2 steps. So the eccentricity is 2 of all my vertices in G. So what that means is my collection G here, my collection of vertices G, are exactly the center of the graph, that everything in the vertex set of G is a central vertex of the graph, and therefore the subgraph induced by these vertices is the center, and it's also G. And that's the proof. So, right, so you may wonder, so now we know every graph can be the center of some other graph. So what about, can a graph be the periphery of another graph? Turns out this one's a little bit harder. I'm actually not going to go quite through all the proof, but I'll state the result. A non-trivial graph G is the periphery of some other graph if and only if, right? So we give a characterization of graphs which are the periphery of another graph, if and only if every vertex of G has eccentricity 1 or no vertex of G has eccentricity 1. So pretty interesting result there that tells us when a graph is the periphery of another graph. All right, so there's center and periphery. I'm going to end this video here, and I'll see you next time.